Okay, first question. Which of these is an electron? An X-ray, a gamma ray, an alpha particle or a beta particle? Well, an X-ray and a gamma ray, they're both photons, electromagnetic radiation, light, which is made of photons. An alpha particle, well, that's 2 neutrons and 2 protons, okay? So it's got a 2+ charge from the 2 protons. An alpha particle is the nucleus of a helium atom, so that's not an electron. It's the beta particle. Beta particles are fast-moving electrons. Okay, which of these will repel an alpha particle? Okay, like I just said, an alpha particle, 2 neutrons, 2 protons, has a 2+ charge. So what repels a positive charge? Another positive charge. So we're looking for something with a positive charge. Okay, a nucleus, that has a positive charge, so it must be that one. Okay, electron, beta particle, that one. Yep, the nucleus of an atom has a positive charge because all nuclei of atoms, or nucleuses, I'm not sure which, have at least 1 proton in them, so therefore they are positively charged. An electron is negatively charged, that will attract an alpha particle. A gamma ray doesn't have a charge, it's a photon, or it's made of photons, so it won't attract or repel an alpha particle. A neutron is neutral, it doesn't have a charge, so it will neither attract or repel an alpha particle. Okay, right. So this is the nucleus of a gold atom. Which of these shows the path of an alpha particle? Okay, again, an alpha particle, just to remind you, it's got a +2 positive charge. So nucleus, like we've just talked about, a nucleus will repel an alpha particle. So that just goes straight past without affecting it. So that can't be right. It's not that one. Here, the alpha particle is being attracted towards the nucleus. Well, that can't be right. Here, the alpha particle is being repelled away from the nucleus, so it's that one. And again, here, the alpha particle is being attracted towards the nucleus. Okay, positive repels positive. Okay, alpha particle, 2+, nucleus, however many pluses. Oh, well, it's a gold nucleus, so I don't know the periodic table well enough to tell you exactly how many protons gold has in it, but it's quite a lot. Okay, alpha particle source. Which of these is an alpha particle source? Okay, skin, muscle and bone. Right, this one goes through your skin, through the muscle and through the bone. So that's very penetrating. That can't be an alpha particle. Alpha particles are stopped by a single sheet of paper. Okay? So, it can't be that one. Can't be that one. That makes it all the way through the skin and muscle. Can't be that one. It makes it through the skin. It must be this one. That must be an alpha particle because it's stopped just by the skin. If a single sheet of paper stops alpha particles, then your skin is thicker than paper, so that will definitely stop alpha particles. So it's that one. All right. Final question. Why use alpha particles in a smoke detector? Right. Well, how do smoke detectors work? They have a little alpha particle source. I'm not exactly sure what they use. I think it's American. And again, I'm not sure if that's how you pronounce it, but it's American something. I'm not sure. Doesn't matter. You've got an alpha particle source, okay? And the alpha particles ionize the air around the source. What does that mean? It means the air particles around the source become charged. That's what an ion is. An ion has either a positive or a negative charge. And the charged air particles allow current to flow inside the detector. When smoke appears, it reduces the number of air particles that are ionized, and therefore the current is reduced, and the detector detects this and sets off the alarm. So alpha particles have to have a good ionizing, or whatever you use in a smoke detector that works this way has to have a good ionizing ability. So it must be that one, okay? Low mass, what does it even mean? Don't know. Short half-life. You don't want the source in a smoke detector to have a short half-life, because you'd set the smoke detector up, leave it, and then fairly soon, because it's got a short half-life, it would go off because the number of alpha particles is reducing rapidly because it's got a short half-life, therefore the ionizing is reducing, therefore the current will slow down, reduce, and it'll set the alarm off. So you want a fairly long half-life for a good smoke alarm. Long range. Alpha particles don't have a high range in air. It's about 5 centimeters. Like I said, alpha particles stop by one sheet of paper and about 5 centimeters of air. So you actually don't want a long range in a smoke detector, because you don't want to get blasted by radiation from this thing in the ceiling. It's meant to be saving your life rather than giving you cancer. Okay, there we go. That's it. Thank you for watching. I hope you found this video helpful. If you did, please click the like button, and it would be a massive help if you could subscribe. It would also be amazing if you could support me on Patreon. All the papers and everything are on my website, drgem.com, and I'm also on social media. Thank you.